In this video I'm going to be going through exercise 1.5 on page 23 of Copeland's Engineering Studies Definitive Guide Volume 2. I'm using the second edition for page numbers. What we're looking at, we're going to solve this truss. We're looking for a specific member, this member X. That's pretty common, and this is why we want to use method of sections, is because method of sections, it allows us to avoid, well, otherwise we'd have to solve 1, 2, 3 joints. Instead we can just do one section in one go. So when we do this, first thing we need to do is we need to find the reaction. So when we find the reaction, which reaction do we find? We can find either RA or RB. Now sometimes we're going to have to find both reactions, but often with trusses you can get away with just solving one. If the question doesn't explicitly ask you to find both reactions, you can just solve one. Why RA? Because RA is a roller. Rollers are simpler. Rollers always give us a perpendicular reaction, whereas pins can be diagonal, and they can have a vertical and horizontal component. That's more complicated. We want to try and keep this as simple as possible. So first thing we're going to do is we're going to try and find reaction A. To find reaction A, we have to take moments about B. Why B? Well, because we have two unknowns. We know that moments equal force times perpendicular distance. I always write force times perpendicular distance in the brackets. If we take moments from B, our perpendicular distance to force reaction B will be 0. So anything multiplied by 0 is 0. 1 multiplies by 0 is 0. A trillion times 0 is 0. So it doesn't matter. Okay, so we're going to go through this equation. We've got the clockwise sum, that's a sigma, of moments measured from location B equals 0. How many forces do we have? We have 1, 2, 3, 4. Now often, textbooks will not include this first part because it's 0. They're like, we don't even care. But me, I like to explain why we're taking moments from point B and then to list out every force. So we've got 1, 2, 3, 4. Yep, 1, 2, 3, 4. Let's have a look. So we're going to say reaction B multiplied by 0 is 0. So I put a line through it to show we don't actually even need that. Then we have RA. Now how far away is RA? 1, 2, 3 triangles. We could use meters if we knew how many meters, but they didn't provide that. So what we can just do is use 3. Now in my previous video I talked about how we could use 3t, but that's actually more difficult. We end up having to cross out the t's later. We can just avoid it and just say we're just using 3. So RA multiplied by the perpendicular distance of 3. That distance between here and here is 3. Now we know that because it's perpendicular, because rollers are perpendicular. Rollers are perpendicular. I've actually restarted this video a couple of times because I misspoke there. Okay, the next four. Now, we said positive. The reason for that is that if we're playing Wheel of Fortune, we're going to spin this wheel. We've got our axis on B, and we're going to turn this. We're going to lift it like a clock. We're going to lift this clock arm. We're going to push in this direction. Which way is it going to go? Well, let's spin the wheel. Okay, that was clockwise, so it's positive. Doing the same thing for 30 is negative, so anti-clockwise. 13 is also negative, right? Also anti-clockwise. What are the perpendicular distances? Well, extending this line all the way through, our perpendicular distance to B is 2.5. The perpendicular distances can be what get people, but luckily here all of our forces are exactly vertical, which makes it really easy. When we start having diagonals, we have to break it into components. We'll worry about that more later. Okay, the next thing here is we have 13, it's half a triangle. So I have 2.5 triangles and half a triangle away. So if we add these together, what we're going to get is we're going to get 3RA. I've moved 3RA over to this side, so it's negative 3RA equals minus 75 minus 6.5. Well, if I already owed $75 and I take away another $6.5, I now owe $81. The two negatives cancel out, which means our assumption, the answer is positive. Therefore, our assumption was okay. Well, I made an assumption at the start. The book did not explicitly say that this reaction A was going up. In some cases, especially with cantilevers, we can have reactions going down. So in this case, the RA was not a given that was up. We made an assumption. That assumption proved to be correct. Now we said 3RA equals 81. If we had three,
there's no one else here. Is that all right?
If we have 3 apples. Right, and that's 3 apples is equal to 81. Well, how much is, if we have 3 apples is equal to 81, how much is 1 apple going to cost? Or Ra is going to be 27.2. Now, for this question, we don't need RB. RB is not necessary for this question because we're going to put our section line through X and we're just going to take the left-hand side. We could have instead, if the roller had been on this side, we just take the right-hand side. We can also solve, if we want, we can actually solve the truss backwards and we should get exactly the same result. Right? If we take the left-hand side or the right-hand side, it doesn't matter which side Vector and Gru steal. It doesn't matter which side, we can still solve, it's the same force internally. Okay, so what I've done is I've redrawn our cut half of the truss. I've got two external forces, 27 and 30, and I have 27, and the 27 is the reaction we found here, and 30 is the external force down. There are forces inside this truss, but we don't care about them. We don't care about those forces because those forces, we don't care about those forces because they're internal members and they're not being cut. These forces, on the other hand, are being cut. Now my thing is, I like to call the distractors P and Q. We should never have more than two distractors. When I say distractors, when we're cutting, our target is X. The other two members that are being cut, sometimes it's useful to name them, so I call them P and Q if we ever have to name them. That's just my thing. Okay, P and Q don't meet, so we're going to use the lone wolf method. Okay, P and Q, they don't meet. If they met, we'd use the meetup method. But because P and Q are parallel, we can't use the meetup method, so we're going to use the lone wolf method. I guess the mnemonic here is you can say meetup is moments, and lone wolf is forces. Right, so what forces are we looking at here? Well, we have P and Q, and we have an unbalanced vertical force. Right, so what we have here is there's a difference between 30 down and 27 up. That difference is 2.8 newtons. Now one of these three members has to take that 2.8 newtons. Somebody has to do it, right? P says, nah, don't do that. I'm just horizontal forces, sorry. Q, yeah, same, I only do horizontal forces. X, on the other hand, X like, okay, I help it. I'm the only one who can do vertical, right? So X is going to, X is going to step up and it's going to be the take on the vertical component. But X is more than the vertical component, right? The vertical, I've actually highlighted this V just to say it's the vertical component that's 2.8. Now, I've made an assumption here as well, right? I've made an assumption when we draw this, we draw everything in tension. We draw everything pulling out and we assume tension. And when I type in this calculation, I say sum of the forces, so assuming positive is up, we say the sum of the forces vertically equals 0. 0 equals plus 2.7 minus 30 minus the vertical component of X. Now, what we end up getting is we get a negative answer. If it's negative, we assume tension. If it's negative, therefore our answer is in compression. Okay, so that means that it's the opposite direction to what we thought. And we can see here this little diagram, where I really like the diagram. I find that that's a much easier way of working. I can see with that diagram that XV has to be going up. The vertical component of X has to be up. And if it's up, that means it's going into the node, and that means it's compression. Right? If it's going up, it's going back into that node, and if it's going into the node, it's compression. So then we have our diagram here. We're going to say, well, if XV is 2.8, how much is X? Well, we know it has to be bigger. Why does it have to be bigger? Because it's the hypotenuse. If it's the hypotenuse, it has to be bigger than the components. So we're going to say 2.8 divided by sine 60, which I know sine 60 in my head is 2.8 divided by 0.66, which is a disco number, equals 3.2 newtons. And because it was the opposite to what we expected, it's in compression. Now, Copeland just identified straight away and said, okay, well, it has to be in compression. The force has to be going up to balance these forces. That's fine. And then says, okay, sum of the forces vertically equals 0. 0 equals 2.7 minus 30 plus x sine 30. Why plus? Because Copeland knows that it has to be going up in order to balance these forces, right? So he's made that assumption to start off with that it's in compression. If you just know that it's sine 60 because of the angle, well, that can help. Some people are happy to do that, and that's how they're happy to solve this.